So based on what we have learned so far in combinational circuit design, we will now design a 4-bit ripple carry adder, and you're looking at the block diagram of the 4-bit ripple carry adder. So we have already designed the full adder here. All we now have to do is to create 4 instances of this full adder, and an extra detail is that we have to connect the output of the the carry out of the first full adder to the carry in of the next full adder, and so on. So once that connection is done, then the components will all be interconnected correctly. Also, we have to take care to feed the inputs correctly. So this, we will use an array. In this case, it's a 4-bit array, and we'll also use the 4-bit array for the sum output also. Right. We could also use a 4-bit array for the carry, which we will do progressively, but initially we'll just say connect these ripple carry adders with wires and get the naive design to work first, and then we will progressively improve the design using more intermediate Verilog concepts. So let me just start off. Yeah. Here RCA 4-bit ripple carry adder. Yeah, so the ripple carry adder will have so sum and carry out, and then A and B 4-bit inputs, and a carry in, which is single bit. Carry out and carry in are single bit. So to declare the 4-bit inputs, all one has to do is to sort of declare an array, and this is what it looks like. So what this indicates is A is a 4-bit element and B is a 4-bit element. They basically just one element. So if you could further do something like this, for example, what this would become now is an array A, and each of the elements in the array is another 4-bit element, right? And this would be a single dimensional array with 4 elements, whereas this declaration here indicates that A is an element with 4 bits. So similarly, the sum output is also a 4-bit quantity, and the other input is of course carry in, and the output is the carry out. We'll go ahead and instantiate the full adder here. So the first full adder, say for example this is phase 0, and what we now have to do is connect the A0 and B0 bits from the A and B inputs to the 0th full adder, and the 0th full adder will generate some least significant bit of sum, that is S0. So this will be sum of 0, right? And so let's take it up and say A of 0 as the first input, B of 0 the second input, carry in of the block as the as the carry in input. So to connect the 0th full adder to the next full adder, we need a bunch of intermediate wires. So let me just declare some of the wires. So from the block diagram, so we are declaring these wires: a wire that connects FA0 to FA1, and then we need a wire to connect FA1 to FA2, and then we need a wire to connect FA2 to FA3. So we need 3 wires. So 0 to 1, 1 to 2 and 2 to 3, and the output from FA0 will have to be drawn out of 0 to 1, right? And the next full adder, input will have to be, the input carry in will have to be connected to the wire 0 to 1. The inputs will be the next pair of bits, and the sum output will be sum of 1, and the carry out will be, then the second one is this, the inputs will be A2, B2, and the output of FA1 carry out, which is 1 underscore 2, and the output from FA2 will be drawn out of W2 underscore 3. The most significant bit FA is generate sum 3 while taking A3 and B3 as inputs, and taking the input from the carry out, the previous full adder, and generating the final carry out of the full adder. So this is, yeah, looks like the interconnections are all done correctly. So this should be the ripple. Yeah. So there is an RCA there. So I yeah, apart from there are no syntax errors, so what that's be done is to give it a full adder also. So that's done. So yeah, so that is so we'll write the test bench for RCA now. Data RCA underscore 4-bit underscore. So I'll just copy the inputs and the outputs and just create equivalent urgent wires for these. Instantiate the 4-bit ripple carry adder here. So call it say RCA1 or something. So let's write out the monitor statement first. We want to print out our keys. To generate the stimulus for the ripple carry adder, we'll use the inbuilt random function. As the sizes of the input increase, the total input possible combinations are also increasing exponentially. So Verilog provides a random system function which returns a 32-bit random signed integer actually. So to generate say unsigned integers, you could use the urandom system function. Here a is a 4-bit number, so we could just assign random to a, and the last 4 bits of the generated random number would get assigned to the our input signal A. Similarly for B, right? So I'll give a delay of say 5 time units. Similarly for carry in, could be, yeah, it could also be random. So, and now we'll feed a few of these, right? So we'll say 5 times. So I've just generated the same thing 5 times. I could either do this, and then I just finish. I could either write this code 5 times, or Verilog provides us a inbuilt construct called repeat, and repeat is basically a bunch of statements that can be repeated any number of times. I've given 10 here. So what happens is any statements that are in between begin and end will be repeated 10 times. That's it. So I remove this extra. Yeah, this is done. So yeah, we've done 2 new things here: generated random inputs and also repeated this sequence of instructions, or this feeding of inputs so many number of times. So let me see if I can yeah, compile this. Okay, so there are no errors. I believe that is all that is needed. I think we are set to run the program. So, okay. So the ripple carry adder inputs are, for example, so here 0011 and 1101 with a carry of 1, and the expected output is, yeah. So yeah, please go ahead and verify if all of these are correct. We now have the naive design of the ripple carry adder working. So the next step is to generalize the ripple carry adder definition. We have sort of hard-coded this 4-bit value, the 4-bit inputs and the outputs here. So what would be useful is to actually make it parameterizable, and Verilog provides this parameter. Verilog provides this inbuilt keyword called parameter, which is equivalent of the hash define constant in the C programming language. So for example, I could just say parameter n equals 4, right? So that and then modify this. So first of all, let me just save this as a new file, and then RCA with the parameter. So this will now be a design for the n-bit ripple carry adder. The inputs remain the same, except the inputs, the size of the inputs and the size of the output sum will change based on the parameter here. So all I have to change is, instead of the hard-coded 3 value, should be n minus 1. Now the real complexity is when we are declaring these internal nets, right? So the internal nets also have to be parameterized in some sense. So we'll let's say I'll create wires. We need n minus 1 wires. There will be 4 ripple carry adders, and we need n minus 1 wires, and modify the code accordingly. Actually, I'll use the first wire to read out carry out of FA0, and the same first wire will be connected to the carry in, and so on. Actually, there is a better way of doing this, but let's just confirm that this works correctly, and then we'll notice a pattern, and that can also be automated. Yeah, so again observe we've not done anything very different in the carry in connection in the connection of carry ins and carry outs. The FA0 carry out is drawn out of W0 via W0, and the FA1's carry in is fed to fed from W0, and same with W of 1 and W. So let's just compile this one. The latest one that was written was a Verilog RCA with the param. System. What is not defined is the FA dot. Okay. So let's see if this works with the same test bench. So let me just instantiate the new As you can see, we are progressing towards complete parameterization of the ripple carry adder, and what we want to build is a n-bit ripple carry adder now. However, these statements from line 14 to line 17 are still hard-coded, so we will make an effort to completely parameterize these two. So in that direction, what would be useful is to actually create an array of wires and not and use the array of wires inside the ripple carry adder to pass the carry ins and the carry outs. So let me see, I think I'll need this much. The plan is to use the array wires wherever possible. So the carry in we will assign to the least significant bit of the wire. So that means this assign statement will connect the carry in input to wire 0, and once that happens, so we will do this, right, connect the wire 0 to the FA0, the first full adder's input, and the output can be drawn out of wire 1, and the input wire 1 will be fed to the next full adder, and its output will be drawn at wire 2, whose input will be fed to the next full adder, and so on. The last full adder, the most significant bit full adder, will receive wire 3 and generate, let's say it generates out of the carry out of wire 4, and if I did assign of W assign carry out to W4, then now you observe this block of statements, they are all now lines 17 to 20 have been expressed in a truly iterative fashion, and that was the objective that we set out to do. Now Verilog provides constructs to generate instances in a loop manner, right? So to do that, Verilog provides this special variable called genVar, which is basically inside a loop. It's basically a loop counting construct to generate multiple instances. We just use this inside a for loop, and let us say I want to create n instances of the full adder, and let me just write that in a begin and an end loop. So the same four statements, basically we just put that inside the loop body. So the other modification that is required is um, to map the inputs and the outputs um, in the instantiation to these local nets over here. So what that means is we explicitly mention that we explicitly mention that the sum output of the full adder, and you can look at the full adder here, right, to the right hand side panel. The sum output has to be explicitly uh, joined to the sum of 0 yeah, we'll modify this in a minute, and let's explicitly sort of connect these local nets to the instance nets first. So the instances net B is connected to local net B of the next task is to replace the array indices with the genvar variable. Observe that this is w of 1, so this will be I plus 1, and this should be I. This these should be enough to do this. Let me check whether this works. Yeah, seems like there is. So let me just run this code. Yeah, it's the same output. So we have achieved the effect. We have achieved the parameterized instantiation effect using the genvar variable and the parameter keyword, right? So this example has shown you the ripple carry adder example had shown you arrays and parameterization and automatic instantiation, and also the repeat loop and random number generation. So this should be additional ammunition for any combinational circuits that you might be coding in Verilog. So that's it for this video.